But the Burmese python is basically a niche that didn't exist yet. So when you've got like a big terrestrial snake that can go anywhere and eat anything warm-blooded, that's a pretty big niche that didn't exist before. So the Burmese is just like adding a ton of predator pressure downhill on trophic levels below it, you know. I just dropped a whole bunch of concepts right there. Everybody know what I mean about that niche being vacant and the invasive moving in easily? Because I was going to do that next. Study goal number 3. You all realize that invasives cannot beat out a native if they're in the same niche. It's not going to happen. Everybody understand that? I'd like to use a car analogy because I'm going to come back to this. Yeah?
So is the invasive and the native just like competing for the same resources the native would always win?
Yeah, and you can think of this as a business analogy. Let's say that they're the exact same niche, okay? That's the big question. Yeah?
Hey, like with the Burmese python, like if you think of the niche, doesn't that create a predator pressure, create like biodiversity, the predator effect, and all that?
Well, it might in the long run, but that assumes that there was already like closely matched species that had, like, the predator pressure is not like a flip it on and it happens right away sort of thing. Like, the predator effect is what happens in the evolutionary time scale as species all kind of evolve as a team in the same setting. You know what I'm saying? A lot of times you just throw in a predator, they'll just eat everything. Okay, what I wanted to say about invasives, I want to use a business analogy. Imagine you're a mechanic, okay? You can imagine if Santa Barbara already has Jiffy Lube and you move into town and you're very specialized, all you work on is early Ferraris. As long as Santa Barbara has enough Ferraris, I'm sure that the Ferrari guy would like to come to you because you're a specialist, and so as a specialist, you can squeeze into a market that only has a generalist. Does that make sense? If you just work on early Ferraris and the only other mechanic in town is a Jiffy Lube, you'll probably be okay starting from scratch. But what happens if Santa Barbara already has a mechanic that specializes on early Ferraris and you're trying to start a new business working on early Ferraris? You're going to add competition, and chances are the local already has a hookup with the UPS guy because they go fishing on Sundays, that the local business already knows the short commute for testing out the suspension, that the local mechanic already has all the client base. And so you don't stand a chance trying to compete with a local who's already set up, right? That's the same thing. You shut up over there. It's not all about you. I'm just kidding. Need some water. Invasive species can't move into an occupied niche. The local's already better at it. They evolved for that local job. So if Santa Barbara had a species just like cane toads and you dropped in some cane toad from Hawaii, the natives are going to be evolved for our climate, which isn't exactly like Hawaii. That Hawaiian cane toad doesn't stand a chance here. You know what I'm saying? If we don't have anything like the cane toad, what gives the invasive the opportunity is the availability of that market, the open niche. And so now we get to the punchline about invasives in number 3. Invasive species really like disturbed environments. Because in a disturbed environment, you've got more empty niches. There's no native that does that. Imagine if you could kick out all the mechanics in Los Angeles. Whatever you want to do, you can get a job in Los Angeles as long as you're a mechanic. Because there isn't a single mechanic left in Los Angeles. Wow. You can specialize in whatever you want, and you can get a job there, no problem. Y'all liking my mechanic specialty metaphors? Because it's not done. I'll be back. I got more. Okay. Number 4, convergent evolution, coming up with similar adaptations because you face similar problems. And divergent evolution, becoming more different over time, adapting to different things. We also call that adaptive radiation. Number 5, we'll look at later today. Number 6, I don't really care unless you want to ask me something. Number 8, what is an ecological island? Give me an example. Don't read the definition. What is an ecological island? Give me an example.
Like a stand of trees in a meadow that is surrounded by a forest.
Yes, that's an ecological. What's another one?
Like a pond in
A what?
a pond in Michigan woods.
Yep, pond in the forest. Yes?
Like an oasis or something, like a desert.
Ooh, yeah! Oasis.
Wouldn't the underwater thermal vents be one?
They probably are, yeah. Underwater thermal vents are almost certainly an ecological island. That's an exceptional example.
What about like a sandbar?
I don't know. I mean, is that ecosystem isolated from its surroundings?
No.
Then I would say not so much. What makes an ecological island is just like Santa Cruz is separated from land by all that water. You have one biome separated from more of the same by a separate biome. So the pond in the woods, that's like a little aquatic thing surrounded by a totally separate terrestrial biome. Or the forest in the meadow, that's like one biome with a totally separate. There's a great example. Anybody here ever been to Irvine, the city of Irvine, California? If you know it well, and I don't know how many of you know it well, but I think some of you play volleyball at University High School, Uni High, which has kind of like a bone-crushing volleyball team, I've heard. So I went to high school there for 2 years, the worst 2 years of my life, by the way. No, really. And Irvine, is the middle of this giant concrete jungle. All the streets are built like freeways, and the speed limit on every avenue is like 65 miles an hour. So everybody gets up to freeway speed, but then there's stop signs every 100 yards. It's like the most wasteful driving. It's like a place built to burn gas. That's Irvine. And in the middle of all that concrete and asphalt jungle with little subdivisions and planned communities and concrete, shopping mall, schools, concrete forever, there's this one pocket of nature in the middle of Irvine. And coincidentally, University High School is right here, and my house used to be right there, so I ride my skateboard through there. And in 2 years of skating to school every day, I had 2 separate mountain lion sightings while on a skateboard on a sidewalk. Because that one little island, that's like Tom Hanks and Castaway. Those mountain lions will never leave.
How big is it?
Anybody know?
Are you talking about the lake or is it?
Yeah, right behind Uni, between University Drive and Uni High.
Yeah, I think I know.
It's on the North Wash side of Turtle Hill or whatever they call it.
Yeah, I don't know. My cousins live there.
Turtle Rock. Yeah. I don't know what it's called either. But there's this I would probably call it maybe 100 acres or something. And there's actually a big park this way and a bunch of farms that way. So it's not perfectly isolated, but there's a freeway, a big avenue, a little avenue, and another avenue. And there's a residential community. So it's pretty darn isolated. Those mountain lions, they're not going to walk through the middle of a residential area for 10 miles to go find another place to hunt. They're stranded castaways. This is an ecological island where you've got little clusters of one biome that are just poof, a little tiny pocket of a separate biome. You know what's really neat? Because of the shape of California, the fact that we've got big old mountains and then a big inside valley trapped by snow, and then snow-capped mountains and desert, we've got all these little islands of habitat. Technically, you might be surprised to know that this chunk of dirt per square mile has more plant diversity than any comparable chunk of land. There is no more place with more species per square mile on average. Indonesia's right on the edge of that. But because we've got so many little pockets, so many little ecological islands, We've got a ton of diversity here. Will you make the backgrounds black, by the way?
Yeah.
And the writing white? Okay, that was a long talk about number 8. Finally, in number 10, I want to talk a little bit. Patterns of diversity. One thing that I want you to remember is if an environment is really sunny and has plenty of nutrients and plenty of water, it's super productive. And you should know this, that high productivity equals high diversity. The most productive ecosystems are the most diverse, because think about it, you'll get more specialized mechanics if there's a lot of cars in town. The more cars there are in town, the more separate car specializations you can support in that economy, right? So if you've got a lot of energy bouncing around an ecosystem, there's a lot of little niches you could break into. High productivity is proportional to high diversity. Also, when climate has a lot of variability, you can't really specialize too much because climate goes very different. So variable climates have low diversity and stable climates have very high diversity. Because if it's stable, you can always count on that one set of conditions that allow you to specialize very, very finely. So let me do this. Productivity is proportional to diversity, and stability, climate stability, is also proportional to diversity. If there are no other questions, now we have to start the biggest study goal in the history of the world. I'm going to get into this. Go ahead, get into this. I'm going to get into this. You go ahead. Get into this. So this is like I hate this part of the class. I kind of love it because I've been a naturalist my whole life ever since I was a little kid, and so like talking nature stuff is cool for me because I'm way into it. It just bums me out when I can tell the kids are like, "Come on, bro, this is getting old." Because like, here's what I got to do in the next like 3 or 4 or 5 days. I have to introduce you to the place where all environmental science happens. Like any environmental science thing we talk about is happening someplace on the planet. So the next 5 days is like, "Hi kids, welcome to Earth. Let me tell you about the Earth." And frankly, I think that's kind of a big undertaking. Everything that we talk about in the United States will happen in some biome, and there's always some little detail about why it's different because it's in Santa Barbara, as opposed to if that happened in Florida. Do you all realize that Americans are extremely undereducated about geography? Have you all heard this? Anybody here talk to people internationally or go to school internationally and they know all sorts of stuff about like which country is where and which capital and history and like what happened in Europe and stuff? This sucks for you. This really sucks for you. Because newsflash, the College Board expects you to be about as knowledgeable as a sophomore or junior in college. And whatever sort of information is required, you're supposed to have. So you got to have a lot more chemistry than you have. You got to be a lot faster with math than you are, and you got to know a lot more geography than you do. So I'm going to try to show you, like, hey everybody, this is a tour of the planet, and you got to learn for every single place this breakdown. 1, 2, 3. physical parameters that create ecological relationships and evolutionary adaptations, and what that means for human interactions with that environment. So for all the biomes, we're going to talk this. What's happening in the physical environment, like rainfall and temperature and sunlight and so on. Then what does that mean for the animals and the bugs and the fish and the birds and how they get along with each other and if there's anything unique going on, and then why that matters to us. So here's a nice example. We have unusually cold water for the latitude and really consistent day length. So our kelp forests are hyper-productive, and as we discussed earlier, that also means they're super diverse. And because of that high productivity and diversity, this is some of the world's most valuable fishing habitat, right here. And you may not know this, but recreationally speaking, this is like a mecca for playing in the ocean. You know, people from Fiji come to Santa Barbara to scuba dive. When I went to Fiji to go diving, the dude on my boat was like, "Oh man, have you been to Anacapa Island?" I'm like, "How the hell do you know about Anacapa Island?" He's like, "Oh man, I was there. It was rad." I'm like, "Dude, you live in Fiji." He's like, "Yeah, you know, but like your area has a lot of stuff." I'm like, "You live in Fiji." So make sure you know that pattern there. The physical to ecological to human interactions. And here we start. We're going to go in roughly this order, from the poles down to the temperate regions. In case you don't know this, everybody must know this vocab, but I can't tell if this is science or just basic. Please look up. There's the polar or Arctic stuff. It's like a ring from 60 to 90, right there. If you take a look at our planet, it's right here, from about 60 to about 90. That wedge at the top, the cap there, and this little wedge right here, 60 to 90. Those are Arctic / polar. Then we've got the temperate regions. Those are right here, that's where we live, between 60 and 30. 60 to 30, like that. That's temperate, and this is temperate. And then between the 30 and the 30, equator to 30 north and equator to 30 south, that's the tropics. So you got your tropical, your temperate, and your polar / Arctic. If you can please look up here, everything in the Arctic is just Arctic. There's just one biome up there. It's either straight ice or it's tundra. Arctic is Arctic, and that's all you get. In the temperate regions, you've got like some scrubby stuff, some grassy stuff, and some woody stuff. In the tropics, then there's different types of forest. There's cloud forest, rain forest, much other. And remember, we're going to talk about all these things about how they feel, what gives it the physical characteristics. These are the two big variables. You've seen the last diagram and you've seen this one. This was homework yesterday, right? Day before yesterday? A lot of my students give the wrong unique variable for the desert. Please look up. You'll notice that the coldest and driest is the white little thing on the edge there, the tundra. It's basically like frozen wasteland. And then everybody knows the hottest and wettest is, like tropical and rainy forest, tropical rainforest, hottest and wettest. But I want everybody to notice what defines the desert. It's not the heat. Look at the range of temperatures for the desert. The desert goes from really hot to really cold. That includes every effing temperature. It's just dry that defines the desert.
What's 30 degrees Celsius?
What?
What's 30 degrees Celsius in Fahrenheit?
30 degrees Celsius in Fahrenheit is like pushing boiling temperature. That's like I'm gonna guess like really high 90s, maybe. Anybody know?
I think the 40s is like.
What's body temperature? Is 32 Celsius, isn't it? That would be
like
98.
low 90s.
Doesn't anybody have a cell phone?
86.
There's an equation.
30 is 86?
Yeah.
30 is 86. Who asked me? Who asked me 30? You asked me 30? 86. Okay. So there's this set of biomes described by those two extremes. Oh, it's great. And so, like I said earlier, you don't really need to copy that because that's already here. You've got that, like, what it's like locally, and then how that shapes ecology and what that means for people. So today I want to start with tundra first, starting at the North Pole. Tundra is that blue stuff. Newsflash! Anybody see other blue?
Like in Mongolia.
Goldfish.
Yeah. There's the great Asian goldfish, the Swedish fish. Anybody know why there's a Swedish fish in the middle of Asia there? Yeah?
Himalayas.
The Himalayas. And there's another, like, gummy worm down there in South America. Like, how do we have Arctic at the equator?
Like a big, huge plateau. Like elevation.
Yeah, the elevation. Anybody know which mountains those are?
Andes.
The Andes. So I want you all to remember that there's two types of tundra. I think your book might have said this, but if not, we're going to get out of the way now.
Arctic and Alpine.
There you go, Arctic and Alpine, or polar and alpine. Alpine is the mountain kind, because it gets super cold because of your elevation. Polar is the other type of super cold. It's not because of elevation, it's because of your temperatures, average temperatures. Yeah, latitude. And in order to understand first of all, tundra, and by the way, later on, a lot of our other biomes too, I gotta ask you why the planet has seasons. And before you try to answer, don't feel bad. Less than 30% of Ivy League college graduates can explain why we have seasons. Less than 50% of science graduates at Ivy League schools can explain why we have seasons. Why?
Because Earth like orbits on the sun on a tilted axis.
Yes, and so what's love got to do with it?
The sun hits it in different places in the extremes.
Sun hits it in different places. Yeah, you're kind of on it.
Like it has an elliptical orbit that makes it like different lengths or distances from the sun, so it gets more or less heat.
So I'll come back to that, but the answer to that is hell no, bro. Way wrong. The wrongest. Don't anybody ever repeat that.
Jeez.
Shut him down.
Never, ever, ever say that again. You're a bad person. Fun fact, we're actually closer to the sun during our winter.
Oh yeah.
But this has nothing to do with it. Anybody else? Guess?
In the summertime, it's more directly straight over Earth, and in the winter, it's closer, but it's at a different angle, probably more on the side.
Like, I believe you may know it, but you're not saying it in a way that someone could learn it. Who else? Come on. Don't make me bring out my model. Yes?
So what modes are like direct sunlight versus like tilted?
You're just not like, yeah, there is an issue of directness.
Is it because the axis always points in the same direction?
Now we're getting somewhere, and so what's that got to do with it?
since the Earth's rotating on two different axes, there's one of them's it's always going to be at the same angle this way, but it's going to be turning. So like when it's at this angle, this part's going to be summer, and then it's going to turn, so this part's going to be summer. Is that sort of?
Door. I like this part of the day. This is like solar flare. We're all gonna die. Sorry, Jesus. Let's see here. First of all, you get a day, and so there's like 3 or 4 things that you're gonna need. You got to keep track of like 1, 2, 3, 4, 5 separate geometrical issues. That's why this is such a difficult thing to explain. Come to think of it, there's really no explanation that you should know that requires 5 separate geometric concepts. You've got 5 separate geometries at play here, and so I can understand why this would be a very difficult challenge for most people to explain. This is more geometry than we keep in our head for pretty much anything. So don't feel bad. Geometry fact number 1, if you were going to write this down in your notes, would be that one rotation around the axis is called a day. So watch. Day. Day. And technically, my gears are accurate, but the Earth has a lot of play on its axis, so a day is actually a lot faster. A day should be going like, but there's a lot of play in the gears here, so that's about a day there. Okay?
I think your Earth's a little too big of one.
Shut up. Second of all, as you get many days happening, we make a rotation around the sun, and we call that a
year.
Very good. So, fact number 1, you've got this thing called a day, which is a single rotation around the axis. And fact number 2 is that spinning Earth is working its way around the sun in what we call a year. So we're going to have to keep track of 2 separate time scales, the days and the years. Don't confuse them. I think that's maybe what you meant about the 2 different axes?
Yeah.
Yeah, we've got this axis and then this axis. Now, to show you why nobody should ever say what Bodhi said. Ever. Ever. Damn it, Bodhi. Our Earth's rotation is, first of all, not a perfect circle. It's kind of shaped like an egg. It's offset ovaloid. So offset ovoid. And the sun is not at the center either. It's off to one side. So there's a time when we're a lot closer and a time when we're a lot further. But you know what? It's not the pattern you would expect. Check out the size of my shaka. That's winter. That's summer. See how my shaka is about an inch off? Anybody know why the distance from the sun has no effect on temperatures on Earth? If Daniel was on fire, I wouldn't break a sweat. I don't mean to say I'm a jerk and I don't care. I mean to say that heat doesn't travel very far. Matter of fact, if Bodhi was on fire, I probably wouldn't even feel it from like right here. And if I had like my marshmallow, I could be like, yeah, now we're cooking. And you know, if I get a little closer, it's like, oh crap, you ruined my marshmallow, Bodhi. But I could be like, sweet spot, and then watch this, you all know how to cook a marshmallow. You go from the sweet spot to ice cold. Because heat doesn't travel very far. You ever know that? In other words, your temperature to the sun makes no difference when you get further than that. Like right there, you're on fire. And right there, it doesn't matter. You're 3 degrees above absolute zero. You're in open space. So all this is all just as cold. The heat doesn't travel very far. Everybody got that?
Aren't farther out planets generally colder?
But not because of the absence of solar heat. They're colder for another reason, which is entirely separate. There's 2 ways to make heat.
Why is the summer hotter than the winter?
Why is what?
Why is the summer hotter than the winter?
That we can do last. But how do we make heat?
Light?
Yeah. You know, like the black sweater, white sweater thing? Anybody know about color theory? Like why black is black and why white is white?
Yeah. What reflects?
Yeah, what reflects and what absorbs. If somebody's wearing a black t-shirt, homegirl, any light that hits her t-shirt is being absorbed by that t-shirt. So I see the absence of light. You might realize that black is the color of darkness. In other words, the absence of light, and light is energy, and her shirt has absorbed all the light. Nothing has bounced back to our eyeballs. We see this patch of darkness right there. Patch of darkness. Cold black heart. Okay. We've got our patch of darkness wearing a patch of darkness over there. And the reason that that shirt will be way hotter in the sun is because all that energy is being captured by the garment, and then that garment is changing the form of that energy and giving it off as heat. Right next to her, Paul's wearing a white shirt, and white is the sum of all colors. In other words, all the light that's hitting him is bouncing off. He's like wearing a mirror. Pretty darn near. And so his mirror is reflecting all the light, absorbing none of it. He'll be pretty cool in the same scenario, because he's not capturing much energy to radiate his heat. Technically, he captures other energy that's not visible in the light spectrum, but Homegirl's capturing way more. Yeah?
You should explain that to Wyatt Dennett, because me and him were having a debate on it, and he thought that that was wrong. And
He'll be in the room today.
yeah.
I'll tell him he's an idiot.
He was saying that your body heat, or like the black reflects your body heat back onto yourself, but it's not about heat, it's just light, right? So it's,
Yeah, I mean, unless you're giving off light,
yeah.
I think he's kind of wrong. Because like wearing a black sweater versus a white sweater in the dark makes no difference, and everybody knows that, I think.
Yeah.
Yeah, okay. Silly Dennett. We all make fun of Dennett. This is fun. Okay. So somebody asked me, though, then why is it hot or something? And this is the punchline. I only get 4 minutes left to make my point. And this makes a really big difference. Really. I want everybody to keep track of 2 separate and confusing patterns of geometry here. You got to think in 3 dimensions, 2 separate variables. Just so you know, a lot of your brains will struggle with this, but you're all capable. Watch me. You can see a little line that divides the sunny side of the planet from the shady side of the planet. Everybody see that?
Yeah.
The light has cut our planet in half. And so 1/2 is getting light and 1/2 is not. And look at that angle. See how that angle is pointing at that wall? Watch this. Now, which wall is that angle pointing at?
That one.
Same one.
Oh.
Okay, fine. Let's move it again.
Which
Which wall am I pointing at? The axis is still pointing that way, right? Everybody look at this. I'm pointing this way. Watch me. Axis stays the same. So wherever the Earth is, that axis doesn't change. Yeah. comes. I got to do this. Because that axis is always going to be pointing at that wall, when you cut the planet in half on these days, you're only capturing a teeny little wedge of the northern hemisphere with sunlight. Only a little bit of the northern hemisphere absorbs sunlight every day, while a ton of the southern hemisphere is absorbing sunlight. Because it's tipped like this, and then you're slicing it in half. You know what I'm saying? You get a lot more of the bottom half when you slice it this way because it's tipped over. Everybody get that? Watch, I'll do it again. That would be the northern, that's the summer solstice for North America. Look at how much of the northern hemisphere is in the sunlight. That's the equator. This is the sunny part. That's way more than half of the northern hemisphere, right? So the northern hemisphere is absorbing a lot more light, and thus giving off a lot more heat. You've got long day lengths, because you're going, all this is going to be exposed to sunlight. That's way more than half the planet at the northern hemisphere. Agreed? But look, in this season, the poor little southern hemisphere is losing again, because they only get this little tiny wedge of sunlight right there. That's all they get. So in the course of a day, that southern hemisphere is only absorbing energy in a very small area, while the northern hemisphere is absorbing a ton. So this is northern summer. More sunlight hitting more land for a longer period of time. And this is the southern winter, less sunlight, hitting a smaller area for a shorter period.
So what explains Antarctica having like 24-hour light?
You can do it right here. Step up here and check me out. Because we're pointing at the sun, watch the North Pole. Everybody watch this. This is the vampire movie, 28 Days of Night. That's like the best vampire movie ever. 30 Days of Night. Watch this. Watch me. Watch. Okay, watch. That little ring, because you're pointing it this way, will always be in the sunny half. So because this is the sunny half on this side, however I spin the planet, that little ring is always going to be in the sun. See how that little ring is always on the sunny half? That's the 30 days of summer. Sunlight. And then, no matter what we do now, that ring has fallen on the shady side. See how all those days are in the dark? 30 days of night. Vampire Central. Then you get the spring and the fall, the equinoxes. That's when you're slicing right across the axis. So the north and the south get the same amount.
Got it.
You all like my demo?
Yeah.
That's pretty good, right? Like, for a $40 little plastic thing? My children love this. When they come visit me at the school, they always want to play with this. Dad, can we play with solar system? Finally, there's your extreme seasonality. "30 days of sun, 30 days of dark, equal and equal."